Dear students, in this video, I'm going to discuss about fluid mechanics first module. Okay, first module is basic concepts and fundamentals. Okay, basic concepts and fundamentals. Okay, in this, we are going to discuss about what are the different fluid properties and numericals related to different fluid properties. Okay, before going to this, first we should know what is fluid. Okay, as you all know, fluid definition. Fluid may be defined as a substance which is capable of flowing. It has no definite shape of its own, but it takes the shape of the containing vessel. Okay, why it will take the shape of the containing vessel? Because if you apply any shear stress on the fluid, it will not offer any resistance. Okay, it will not offer any resistance. Okay, that means if you apply any shear stress, this will not uh, offer any resistance. Because of this, okay, this will take the shape of the containing vessel. Okay, shape of the containing vessel. Okay, this is the definition of the fluid. A fluid may be defined as a substance which is capable of flowing. It has no definite shape of its own, but it takes the shape of the containing vessel. Okay. Then again, actually in fluid there are two types. Okay, one is liquids and one more is gases. Okay, what is liquids? Actually, liquids we can't compress easily. That's why we are calling that as incompressible in nature. Okay, all liquids are incompressible in nature. Why? Because if you apply any pressure on the liquid, okay, for example, if you consider water or if you consider oil, okay, you can't compress easily. That's why we are calling all liquids are incompressible in nature. Okay, incompressible in nature. And again, gases. Okay, gases you can compress very easily. That's why we call gases are compressible in nature. Okay, compressible in nature. And one more point I want to mention about fluids. Okay, just now I told you fluid will not offer any resistance to applied shear force. It will occupy the shape of the container. Okay, but at the same time, whenever the fluid is flowing, actually fluid will flow layer by layer. For example, if you consider whenever the fluid is flowing through the pipe or through channel, okay, what will happen? That fluid will flow layer by layer. That we can't see actually. Fluid will flow layer by layer. Whenever it is flowing layer by layer, what will happen? Okay, from one layer to another layer, there is a shear stress. Okay, from one layer to another layer, there is a shear stress. Okay, see here you can observe, but it does not mean that the fluid do not offer any resistance to shear stress. In fact, as the fluid flows, there exists shear stress, okay, shear stresses between the adjacent layers, which results in opposing the movement of one layer over the other layer. That means whenever the fluid is flowing through a pipe, okay, that will flow layer by layer. Okay, then what will happen? One layer will offer resistance to another layer. Okay, because of velocity difference. Okay, because of velocity difference, that means okay, if you consider any fluid at rest, okay, any fluid at rest, that will in that there is no shear stress. Whenever the fluid is flowing, that time what will happen? There is a shear stress between the fluid layers. Okay, from one layer to another layer. Okay, so here you can observe. It is important to note that when a fluid is at rest, no shear stress can exist in it. Why? Because whenever the fluid is at rest, okay, that will not move. Then again, there is no movement of the fluid layers. Because of that, there is no shear stress between the fluid layer. Right. Okay, this is the definition of the fluid. Then again, if you come to types of fluids, just now I told you there are two types of fluids. Okay, here you can observe a fluid can be classified into two groups. Okay, that is liquids and gases. Liquids are difficult to compress under the action of external pressure, and hence they are considered as incompressible. On the other hand, gases can be compressed much easily. Okay, under the action of external pressure, and when the external pressure is removed, it expands. Okay, that is liquids and gases. All liquids are incompressible in nature. Incompressible means you can't compress, and all gases are compressible in nature. Okay, and again, if you come to fluid mechanics definition, just now we understood what is fluid. Fluid is a substance which offer no resistance to applied pressure or applied shear stress. Okay, it will take the shape of the container and it can easily flow. Okay, that is the definition of the fluid. And again, classification of the fluid. There are two types of fluids. One is liquids and one is gases. Okay, one more is gases. Liquids are incompressible in nature. Gases are compressible in nature. Then, if you come to definition of the fluid mechanics, okay, in this fluid mechanics, what you are going to what you're going to study. Okay, fluid mechanics is a branch of science. Okay, fluid mechanics is a branch of science which deals with the behavior of the fluids at rest as well as in motion, as well as in motion. That means actually in fluid mechanics there are different types of branches are there. One is fluid statics, one more is fluid kinematics, and one more is fluid dynamics. Okay, fluid dynamics. In fluid mechanics, we are going to study behavior of the fluid. For example, when the fluid is flowing, how that will behave, what is the velocity, what is the acceleration, what is the pressure, what is the density. Then when the fluid is at rest, what is the pressure. Okay, that and all we are going to study in this fluid mechanics. Okay, this is the definition. Fluid mechanics is the branch of science which deals with the behavior of the fluid at rest as well as in motion. Okay, this is fluid mechanics definition. Then, if you come to different types of fluid mechanics, okay, different types of fluid mechanics. Just now I told you, see, fluid statics, fluid kinematics, one more is fluid dynamics. So, what is fluid statics? The study of fluids at rest is called fluid statics. Okay, that means fluid statics is nothing but okay study of behavior of the fluid whenever the fluid is at rest. Okay, whenever the fluid is at rest, that means that is fluid statics. Then what is fluid kinematics? See, in case of fluid kinematics, okay, we are going to study behavior of the fluid when the fluid is in motion. Okay, when the fluid is in motion, but we will not consider forces causing the motion. See, for example, you people know whenever the fluid is flowing from one point to another point, simply it will not move. Because of pressure difference only, it will move. Okay, you people know all the fluids will move from higher pressure region to lower pressure region. Okay, higher pressure region to lower pressure region. That means there is a pressure difference. Because of that pressure difference only, there is a movement of the fluid, right? In this fluid kinematics, we are going to study behavior of the fluid when the fluid is in motion, and if the forces are, and if the pressure forces are also considered for the fluids in motion, then it is called, that is fluid dynamics. Okay, I'll tell you what is fluid kinematics. In case of fluid kinematics, we are going to study behavior of the fluid when the fluid is in motion, but we will not consider forces causing the motion. That is fluid kinematics. Then what is fluid dynamics? Okay, fluid dynamics. In case of fluid dynamics, what we will consider? So in case of fluid dynamics, also we are going to study the behavior of the fluid when the fluids are in motion, and we will also consider what are the forces causing the motion. What are the forces causing the motion? That is nothing but fluid dynamics. Okay, fluid dynamics. Okay, now we have discussed about what is fluids, what is different types of fluids, then again what are the different types of branches of fluid mechanics. Okay, just I'll summarize. Fluid is a substance. Okay, it can easily flow and it will not offer any resistance to applied shear stress. Okay, applied shear stress. But whenever the fluid is in motion, okay, what will happen? There is a resistance between the fluid layer. Because of this resistance, there is a shear stress between the fluid layers. Shear stress between the fluid layers whenever the fluid is in motion. Okay, then again, if you come to types of fluids, there are two types of fluids, that is liquids and gases. Liquids are incompressible in nature. That means you can't compress easily. Gases are compressible in nature. You can compress very easily, right? Then again, different types of fluid mechanics branches. Okay, first, what is fluid mechanics? Fluid mechanics is a branch of science. Okay, we are going to study behavior of the fluid when the fluid is in motion. When the fluid what is fluid mechanics? In case of fluid mechanics, we are going to study behavior of the fluid, behavior of the fluids when the fluid is in motion and when the fluid is at rest also. And different types of fluid mechanics. One is fluid statics. We're going to study behavior of the fluid when the fluid is at rest. That is fluid statics. And fluid kinematics. Okay, we're going to study behavior of the fluid when the fluids are in motion, but we will not consider forces causing the motion. That is fluid kinematics. Then fluid dynamics. What is fluid dynamics? In the fluid dynamics, we're going to study behavior of the fluids when the fluids are in motion, and we will also consider forces causing the motion. We will also consider forces causing the motion. These are the different types of fluid mechanics. Okay, we are going to study all these different types of fluid mechanics in fluid mechanics subject. Okay, then different types of fluids. Okay, actually there are different types of fluids are there. Okay, to explain this, we will plot a graph, that is shear stress versus velocity gradient. Okay, this is shear stress term and velocity gradient on x-axis, that is du by dy. Okay, du by dy. That means how the velocity is varying, with respect to distance, Okay, what is ideal fluids? Okay, ideal fluids, you can observe here there is no shear stress. Okay, ideal fluid means there is no shear stress. Ideal fluid is nothing but it is a type of fluid which offer any property of the fluid, okay, which does not possess any properties of the fluid, okay, which does not possess any properties of the fluid. That means actually this is imaginary fluid. Okay, ideal fluids are imaginary fluid. This is not available in nature. Why? Because any fluids available in nature are example for real fluids. Okay, example for real fluids. Okay, whatever the fluids available in nature which possess all the properties. For example, viscosity. For example, density, then again weight density, then specific gravity. Okay, which offers that means which possess all the properties. But ideal fluids are imaginary fluids. Okay, this is not available in nature. Okay, it's not available in nature. Here you can observe. See, there is no shear stress. Okay, there is no shear stress. That means zero shear stress in case of ideal fluids. Okay, ideal fluids are imaginary fluids. This is not available in nature because it does not possess any properties of the fluid. See, for example, whenever the fluid is having viscosity means definitely there is a resistance whenever the fluid is flowing. But in this case, you can observe zero shear stress. That means there is no shear stress in case of ideal fluids. This is not available in nature. Then if you come to real fluids, what is the real fluids? Real fluids means whatever the fluids available in nature are example for real fluids which offers all the properties of the fluid. Okay, properties of the fluid. Then again, if you come to Newtonian fluid, okay, what is Newtonian fluid? This is Newtonian fluid. Newtonian fluid. What is Newtonian fluid? In case of Newtonian fluid, what will happen? See, you can observe here. See, the shear stress is directly proportional to velocity gradient. In case of Newtonian fluid, shear stress is directly proportional to velocity gradient. Or we will say one more definition: whatever the fluids obeying Newton's law of viscosity are example for Newtonian fluids. Okay, whatever the fluids, what is that which obeys Newton's law of viscosity? We call that as Newtonian fluids. Or simple definition: in case of Newtonian fluids, shear stress is directly proportional to velocity gradient. Okay, that is Newtonian fluid. That means linear. How the variation is happening, shear stress and velocity gradient variation is happening linearly. Okay, that is Newtonian fluid. What is non-Newtonian fluid? In case of non-Newtonian fluids, what will happen? Shear stress is not directly proportional to velocity gradient. Here you can observe the variation. The variation is not linear. Okay, shear stress is not directly proportional to velocity gradient. That is non-Newtonian fluids. Then again, ideal plastic fluids. What is ideal plastic fluids? Here you can observe up to some extent. Okay, up to some extent there is no variation. Okay, there is no variation. That means, see, if you apply any shear stress to fluids, okay, up to some extent that will not move. Okay, up to some extent that will not move. After some extent, okay, when it reaches yield value, okay, that will start flowing. Whenever the fluid is flowing only, you will get velocity gradient. Okay, that means variation of velocity with respect to distance. Okay, with respect to distance. Okay, that means, see, in this case you can observe from this point to this point there is no movement of the fluid. Okay, you start applying the shear stress, there is no movement of the fluid. Okay, then what will happen? From this point, okay, when it reaches the yield value, okay, from this point it starts acting as Newtonian fluids. Okay, it starts acting as Newtonian fluid. That means after this point, shear stress is directly proportional to velocity gradient. Okay, shear stress is directly proportional to velocity gradient. That is ideal plastic fluid. Here, definitions are there for all the fluids. I'll show you. Okay, first I'll explain one more. Thixotrophic fluid. In this case, also same thing. Up to this point, there is no movement of the fluid. Okay, when it reaches yield value, then shear stress is not directly proportional to velocity gradient. That is thixotrophic fluid. And what is ideal solid? You can observe here. Ideal solid means it will not move. Then see, if you apply any shear stress, apply any shear stress, there is no movement of the fluid. That means velocity gradient is zero. That's why this will come on this line. That is ideal solids. Okay, ideal solids. Here, if you come to definitions, see here ideal fluid. Ideal fluids have no viscosity. See here you can observe ideal fluids have no viscosity and surface tension, and they are incompressible. These fluids do not exist in nature. That means ideal fluids does not possess any properties. Any properties of the fluid. Not only viscosity, not only surface tension. For example, density. Any other properties it does not possess. That is ideal fluid. Okay, that is actually that does not exist in nature. Okay, real fluids, these fluids have properties like viscosity, surface tension, compressibility, etc. And hence during the motion certain amount of resistance is always offered by these fluids. All these fluids in actual practice are real fluids. For example, if you consider water, oil, diesel, petrol, all these fluids are example for real fluids. Okay, here you can observe Newtonian fluid. Okay, Newtonian fluid. What is Newtonian fluid? Newtonian fluid, a real fluid in which the shear stress is directly proportional to the velocity gradient is called as Newtonian fluid. Here you can observe shear stress is directly proportional to du by dy, velocity gradient. That means velocity variation with respect to distance. That is Newtonian fluid. Okay, example air, water, etc. See, non-Newtonian fluid, I already explained with the help of the graph. Simply, I'm telling you the definitions. A real fluid in which a shear stress is not proportional to the velocity gradient is called as non-Newtonian fluid. Okay, you can observe, see, tau is equal to mu into du by dy. Okay, that is for Newtonian fluid. Here, du by dy to the power of n, that is for non-Newtonian fluids. Examples also, here we mentioned, that is milk, paper, pulp, etc. Next, ideal plastic fluid, a fluid in which shear stress is more than the yield value, and thereafter the shear stress is directly proportional to the velocity gradient. That means what? Up to some extent, whatever the shear stress you apply, okay, any shear stress you apply, okay, till that point there is no movement of the fluid. Okay, after that point, then what will happen? Shear stress is directly proportional to velocity gradient. That is nothing but ideal plastic fluid. Okay, ideal plastic fluid. Then is a thixotrophic fluid, a fluid in which shear stress is more than the yield value, and thereafter the shear stress is not proportional to the velocity gradient. Okay, that is thixotropic fluid. Okay, these are all the different types of fluids. Or sometimes they'll ask this question for 6 to 7 months. Okay, this is also very important. Okay, guys, next very important, that is properties of fluids. Okay, from here we are going to study what are the different properties of the fluid. Okay, till now we have discussed about what is fluid mechanics, and what are the different branches of fluid mechanics, and what are the different types of fluids. Okay, next we are going to study about properties of fluid. See, first property of the fluid is mass density. Okay, here you can observe. See, this is mass density. Okay, the symbol is rho. Okay, for density or mass density, symbol is rho. Okay, one more name, density or specific mass. Sometimes they'll ask you what is specific mass. Okay, don't get confused. So specific mass is nothing but mass density. Okay, mass density. Okay, come to definition. It is the mass per unit volume of the fluid. Okay, it is defined as the ratio of mass per unit volume. Okay, mass per unit volume. Okay, now what is the meaning of this? Say, for example, if you consider 1 meter cube. Okay, for example, if you consider 1 meter cube volume, in that 1 meter cube volume, how much mass you can put? Okay, how much mass you can put? That is nothing but density. See, this density is not same for all the fluids. Okay, density for water is different, density for air is different, okay, density for oil is different, density for petrol is different. Why? Because that depends on how much mass you can put per unit volume. Okay, how much mass you can put per unit volume. Right? For example, if you consider air, the density is very, very less, 1.2 kg per meter cube. That means in 1 meter cube, you can put only that much mass. Okay, that much mass. See, for example, water, if you consider in 1 meter cube, you can put more mass. That's why we are getting for water 1000 kg per meter cube. Okay, 1000 kg per meter cube. That means what is definition of mass density? Just remember this. Okay, it is defined as the ratio of mass by volume. Okay, it is defined as the ratio of mass by volume. See here, density of water is 1000 kg per meter cube. Rho of liquid constant. See why? Because just now I told you whenever I was explaining different types of different types of fluids, liquids are incompressible in nature. okay, incompressible in nature. Because of that, if you can't compress, okay, if you can't compress means you can't change volume. Okay, because of that, there is no change in density. There is no change in density. Density of liquids always constant. Okay, if you want to compress also, you can change very little amount. Okay. Because of that, we will say density of liquid is constant. Density of gases changes with pressure and temperature. That means if you want to compress gases, you can compress, but what will happen? The pressure will increase. The pressure will increase. Because of that, we are telling density of gases changes with pressure and temperature. With pressure and temperature, right? See, this is first property, that is mass density. And density of water, that is constant value 1000 kg per meter cube. Sometimes in the problem they will not give you density of water. If they don't give also, you have to remember this value, density of water, which is equal to 1000 kg per meter cube. Okay, 1000 kg per meter cube. Next is weight density. Okay, next is weight density. And one more name is there, that is specific weight. Okay, that is specific weight. And one more thing I forgot to mention. What is the unit of what is the unit of what is the unit of density? Density unit is kg per meter cube. Here you can observe mass unit is kg and volume unit is meter cube. Okay, density unit is kg per meter cube. Remember, density is defined as the ratio of mass by volume. Then the unit of density is kg per meter cube. Okay, the next very important property of the fluid is weight density. Okay, weight density. You just consider small w, okay, small w, or you can consider gamma also no problem. Gamma also no problem. Okay, this is one more name is there for this. That is specific weight. Weight density or specific weight. Weight density or specific weight. It is a weight per unit volume of the fluid. Okay, mass density is mass per unit volume. Weight density is weight per unit volume. Okay, how much weight you can put per unit volume for 1 meter cube? How much weight you can put? That is nothing but weight density. Okay, weight density. See here you can observe small w. Okay, that is weight density. Or you can use one more notation, that is gamma also. Sometimes in some textbook they used small w. Okay, sometimes in some textbook they used gamma. Okay, both definitions are same. That is weight by volume. That is W, weight by volume. Okay, weight unit you people know, that is Newton, and volume unit is meter cube. Then unit of weight density is Newton per meter cube. Okay, unit of weight density is Newton per meter cube. That is the definition of weight density or specific weight. Okay, next property of the fluid. Next is relationship between mass density and weight density. Actually, these formulas are required to solve the numericals. Okay, to solve the numericals. Okay, that's why we're telling only relationship between mass density and weight density. See, first we'll write weight density formula. Okay, what is weight density? Weight by volume. Okay, weight density is weight by volume. Okay, then this weight we can write as mass into acceleration. Okay, weight we can write as mass into acceleration. Okay, mass into acceleration, then divided by volume. Okay, here you can observe weight density small w, which is equal to weight by volume. In place of weight, you just write m into g. Then you write volume as it is. We know m by v, mass by volume is nothing but rho. Correct? Na? That is density. Then in place of m by v, you can write rho. Then you will get what is that? Weight density or specific weight, which is equal to rho into g. Okay, specific weight which is equal to rho into g. Okay, this is the relationship between mass density and weight density. Then if you want to calculate weight density of water, see here you can observe weight density of water, which is equal to density into specific gravity. Here you can observe density into specific gravity, that is density of water into g. Okay, then density of water we know, that is standard value 1000 into g value also we know 9.81. Then we will get weight density of water, which is equal to 9800 Newton per meter cube. This is weight density of water. Okay, weight density of water. This is the relationship between weight density and mass density. Okay, the next property of the fluid is the next property of the fluid is specific gravity or relative density. Okay, specific gravity or relative density. What is the meaning of relative density? As the name itself indicates, relative means we are comparing one density with another. Okay, one density with another. Here you can observe specific gravity definition, that is density of the fluid divided by density of the standard fluid. Okay, density of the fluid divided by density of the standard fluid. Okay. Or one more definition is there, that is weight density of the fluid divided by weight density of the standard fluid. Okay, weight density of the standard fluid. See, here this is the definition for specific gravity. For this specific gravity, there is no unit. Why? Because density, unit is same. Okay, kg per meter cube, kg per meter cube. Okay, it will get cancelled. You will not get any unit for specific gravity. See, for example, when you are calculating specific gravity of petrol or specific gravity of diesel. Okay, petrol and diesel are example for liquids. Then what is the density of standard fluid? See, in case of liquids, here you can observe, for liquids, standard fluid is water. For liquids, standard fluid is water. For gases, standard fluid is air. See, whenever you are calculating density of liquids, you have to consider standard fluid as water. Standard fluid as water. See, this is specific gravity or relative density. Okay, next is viscosity. Next property of the fluid is viscosity. Okay, what is viscosity? See, you people know, if you consider water and oil. Okay, water and oil. Water can easily flow compared to oil. Okay, water can easily flow compared to oil. Why? Because water viscosity is less compared to oil viscosity. Okay, oil viscosity. Because of that, okay, what is viscosity? Viscosity will offer resistance to the movement of the fluid. Okay, resistance to the movement of the fluid. Here you can observe viscosity definition. Viscosity is defined as the property of the fluid. Okay, property of the fluid. Obviously, this is the property of a fluid which offer resistance to the movement of one layer of fluid over another adjacent layer of the fluid. Okay, over another adjacent layer of the fluid. See, just now I told you. Just now I gave you an example. Water and oil. See, in case of oil, because of more viscosity, more resistance, that's why it will not flow easily. In case of liquid, okay, in case of that means water, okay, viscosity is less, that's why it can flow very easily because the shear stress between the fluid layer is less. Okay, shear stress between the fluid layer is less. See, for example, we can consider this example. Okay, you can consider this example. See, just consider y-axis distance and x-axis velocity. Okay, x-axis velocity. You just consider one plate. Okay, just consider one plate. See, see, if you keep any plate, okay, if you keep any plate, and again you just consider air is flowing like this, or water, you can consider anything, air is flowing like this. See, whenever the air start flowing over this plate, okay, whenever the air start flowing over this plate, the very first layer of the fluid will stick to this solid boundary. Okay, stick to this solid boundary. Why? Because see, here you can observe, this is stationary plate. This is stationary plate. Whenever this is stationary, okay, that means this is not moving. That in that case, okay, whatever the air flowing over this plate, okay, the very first layer, I already told you, whenever the fluid is flowing, that it will flow layer by layer. Okay, layer by layer, that we can't see actually, layer by layer. The very first layer will stick to solid boundary. Then what is the velocity of that? Velocity of that first layer is zero. Velocity of that first layer is zero. Okay, then again second layer. Okay, second layer. Okay, second layer, what will happen? That will start, or that will start moving in forward direction. Okay, that means this will start flowing in this direction. But at the same time, okay, this is stationary. The first layer is stationary, that will try to pull the first layer in opposite direction. That means that will try to pull the second layer in opposite direction. Because of that, okay, just assume the first layer velocity is 0, then second layer velocity is 2 meter per second. Why this is 2 meter per second? So just consider here the free stream velocity is 8 meter per second. Okay, 8 meter per second. Whenever this 8 meter per second velocity is flowing over this plate, the first layer velocity is 0 because that will stick to solid boundary. Then because of this low velocity, this will try to pull the second layer in the opposite direction, but this will try to move in forward direction. Because of this shear stress, okay, that means one is this way and one is this way. Okay, then there is a shear stress between the fluid layer. Because of that shear stress, this velocity, second layer velocity, will decrease. Then this second layer will try to pull the third layer in the opposite direction. Why? Because this velocity is 2 meter per second. This will try to move in 4 meter per second. Then what will happen? This velocity also decreases. Okay, this velocity also decreases. Then what will happen? Here also, between second and third layer also, there is a shear stress. Here you can observe third layer. Okay, there the velocity is little more compared to third layer. Okay, see here you can observe 0, 2 meter per second, then 4 meter per second, then 6 meter per second. After some extent, the velocity which is equal to free stream velocity. What is free stream velocity? Free stream velocity is nothing but velocity of the air flowing. Okay, that means atmospheric air velocity. Okay, atmospheric air velocity. Okay, what I want to convey you people is, see, whenever the fluid is flowing, okay, whenever the fluid is flowing, in between the fluid layer there is a shear stress. Okay, because of that shear stress, what will happen? Okay, there is a resistance. Okay, there is a resistance between the fluid layer. Okay, because of that, there is a shear stress. Okay, that means fluid particles will try to move in forward direction because of viscosity. There is a resistance for the movement of that fluid layer. That is because of what? That is because of viscosity. Here you can observe viscosity is defined as a property of a fluid which offer resistance to the movement of one layer of fluid over another adjacent layer of the fluid. That means first layer will try to offer resistance to second layer will try to offer resistance to third layer will try to offer resistance to fourth layer. But here you can observe the effect of this first layer goes on decreasing. Okay, because of that velocity is increasing. Okay, here you can observe some okay, here you can observe explanation. When two layers of a fluid, a distance dy, here you can observe, see, two layers, if you consider the distance dy apart, move one over the other at different velocity du. See, this is moving with velocity u, and this is moving with velocity u plus du. At different velocities, say u and u plus du as shown in the figure. The viscosity together with relative velocity. Okay, because of viscosity also, because of relative velocity also. Relative velocity means difference in velocity u and u plus du causes a shear stress acting between the fluid layers. The top layer causes a shear stress on the adjacent lower layer, while the lower layer causes a shear stress on the adjacent top layer. Why? Because the top layer will try to move in forward direction, the bottom layer will try to pull the second layer in the opposite direction. Because of this, there is a shear stress. Then this shear stress is proportional to the rate of change of velocity with respect to distance. Y means in vertical direction. It is denoted by symbol tau. Tau is nothing but shear stress between the fluid layers. Okay, whenever the fluid is moving with different velocity, u and u plus du, and which is having some viscosity. Because of that, there is shear stress between the fluid layer. That we can write like this: the shear stress developed between the fluid layer is directly proportional to velocity gradient. Tau is directly proportional to du by dy. You can observe here du by dy, right? Tau. Then to remove this proportionality constant, we are using proportionality constant, and is known as coefficient of dynamic viscosity, or only viscosity. Here you can observe tau is equal to mu into du by dy, right? Then if you want to write unit for mu is nothing but dynamic viscosity. Mu, see what I am writing, I am writing for mu is equal to tau divided by du by dy. Okay, tau divided by du by dy, right? Then unit of mu, just write unit for all the things. That is, tau unit is Newton per meter square, du velocity unit is meter per second, then distance unit is dy unit is meter. Then what we will get? Newton second per meter square. Newton second per meter square is unit of dynamic viscosity. Okay, unit of dynamic viscosity. Here you can observe SI unit of mu. Okay, SI unit of mu, that is Newton second per meter square, or Newton per meter square is nothing but Pascal. Then second you write as it is Pascal second. Okay, both are same, Newton second per meter square or Pascal second. Then in MKS unit, okay, in MKS unit, mu unit is kg force second per meter square. Actually, in MKS unit, okay, MKS unit will write force unit as kg force. Here in SI unit will write force unit as Newton. Here in MKS unit will write force unit as kg force. That's in place of Newton we are writing kg force second per meter square. One more is there, that is CGS unit. Okay, CGS unit. Okay, that is mu unit is dyne second per centimeter square. Actually, CGS, that means centimeter gram second. This is meter kg second. Okay, meter kg second. This is centimeter gram second. Okay, that means we'll write all distance in centimeter, then all weight in gram, then time in second. That is dyne second per centimeter square. Dyne is unit of force in CGS. Dyne is unit of force in CGS. Right. One dyne centimeter per second square is nothing but poise. Dyne second per centimeter square is nothing but poise. 1 poise which is equal to 1 by 10. Okay, this is the conversion actually. See, in the problem sometimes they'll give in terms of CGS unit, but usually to solve the numericals we'll use SI units only. To convert this poise into SI unit, we are using this conversion, that is 1 poise which is equal to 1 by 10 Newton second per meter square. Okay, 1 dime second per centimeter square is nothing but 1 poise which is equal to 1 by 10 Newton second per meter square. Okay guys, you have to remember this. This is the conversion, 1 poise which is equal to 1 by 10 Newton second per meter square. Newton second per meter square. Next, 1 centipoise. 1 centipoise is equal to 1 by 100 poise. 1 by 100 poise. Okay, till now, whatever we discussed is related to dynamic viscosity. Next is kinematic viscosity. What is kinematic viscosity? Kinematic viscosity symbol is mu. Okay, this is nothing but mu. Dynamic viscosity symbol is mu. Okay, mu. See, I will show you what is mu. Mu. See, this is mu. Okay, this is mu. This is the dynamic viscosity symbol, and kinematic viscosity symbol is mu. Okay, kinematic viscosity symbol is mu. See, this is mu. It is defined as the ratio of dynamic viscosity of the fluid to the density of the fluid. Okay, just remember this. Mu is equal to mu by rho. Mu is defined as the ratio of dynamic viscosity to the density. Dynamic viscosity to the density, that is dynamic viscosity divided by density. And if you come to unit of mu, actually in fluid mechanics, you should remember unit of all the fluid properties. For example, density kg per meter cube, then weight density Newton per meter cube, then again dynamic viscosity Newton second per meter square, then next is kinematic viscosity. See, if you want to derive unit for kinematic viscosity, first you write unit for mu. What is unit for mu? That is Newton second per meter square. Unit for mu is Newton second per meter square. Then rho, that is density unit is kg per meter cube. Kg per meter cube. To simplify, what I am doing is in place of Newton, you people know Newton, that is force, Newton second law of motion. F is equal to ma. Okay, F is equal to ma. That is nothing but force is equal to mass into acceleration. In place of force, that means in place of Newton, what I am writing, m into a. Means mass into acceleration. That is kg meter kg meter per second square. Okay, kg meter per second square. That is the unit of mass. Unit is kg. Acceleration. Okay, that is meter per second square. Kg meter per second square. In place of Newton, you can write kg meter per second square. Then as that is second, you write as it is divided by meter square. Then divided by kg meter cube. Then if you simplify this, you will get unit of mu, that is meter square per second. Meter square per second is unit of kinematic viscosity in SI unit. Unit of kinematic viscosity in SI unit. Next, in CGS unit, CGS is nothing but centimeter gram second. That is unit in CGS unit. The unit of nu. Unit of nu is centimeter square per second. That means you have to write distance in terms of centimeter. That's all. Centimeter square per second. One more name is there for centimeter square per second. That is Stokes. 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 One stoke or 1 centimeter square per second is nothing but 10 raised to minus 4 meter square per second. Actually, this is the conversion from unit to CGS unit to SI unit. Okay, CGS unit to SI unit, that is 1 centimeter square per second, which is equal to 10 raised to minus 4 meter square per second. Okay, that is, and one more is there, 1 centistoke, that is equal to 1 by 100 stoke. Okay, 1 centistoke is equal to 1 by 100 stoke.